Thomas.
Okay, yeah, good morning, everyone. So it's 11:30, so let's begin our online class. So can you guys hear my voice? Just want to check
Yes.
it. Okay, so you can also see the slide, right? I think so, right? Okay. So yeah, it's already recorded. So let's begin. So yeah, week 3 is a home-based learning. So we are doing online, and yeah, it's already recorded. So you can see the recording after the class, and I also upload in the NTUlearn, so as you wish. And also I will upload the slide as well. Okay, so yeah, last week we solved the 3 questions about electronic configuration of the carbon and also in the silicon. And we used the EK diagram to, solve the 2 types of questions. So first one is whether among these two, which has a lighter or heavier mass. So we can determine by looking at the slope or curvature of this either conduction band for the electron or the valence band for the hole. And also we study about direct and indirect semiconductor. So direct semiconductor can emit the photon, which is light. And this indirect semiconductor release this energy by, heat, which is the phonon. So this is a concept we studied the last week. And this week we have several questions about intrinsic and extrinsic semiconductor. So I will also show the question and the doing some overview of the content, and we are going back to the question. Okay, so let's do it. I will turn on the slide. Okay, is it clear? Can you see it? Okay. Okay, yeah, this is an overview of the topic, and we are week 3. So we are talking about intrinsic and extrinsic semiconductor. So the first question is about the work function. So this concept, work function, we study this probably week 9 or week 10 when we study bipolar junction transistor. But yeah, this one is just concept you can see. So this one is energy, which refers to minimum energy we need to remove electron from the material. So this one, we have a two material like the gold. So gold has a 4.9 electron voltage and cesium has a 1.9 electron voltage. And we calculate the maximum wavelengths of the light for photoelectric emission of electron for these two type of the metal. So this one easy way to understand is that to the emit the photon, we need this type of energy, like 4.9 electron voltage for the gold and 1.9 electron voltage for the cesium. So if we provide this energy, then this photoelectronic emission of the electron can be possible. Okay. And any question, you can raise your hand and stop me, or you can leave a message in, in the chat room, so I can get back to you. Okay, so yeah, this one is an EK diagram we studied before. So the top side, as you know how we call this, right? This is a conduction band for the electron. The bottom one is a valence band for hole. So I can hear some sound. Let me check. Okay, any message? Okay, no. Okay, so this is a conduction band for the electron, and this is a valence band for the hole. And as we know that this is a conduction band, so this is a lot of energy, line. So this one is we call this conduction band instead of the conduction energy line. And this one is the smallest conduction energy, so we call this minimum conduction band. And this one, we call this maximum valence band. The energy difference between minimum conduction band and maximum valence band, we call this band gap energy. So this EK diagram looks a bit complex, so we simply use this band diagram. So you can clearly see how we can relate these two. So this one is, again, the minimum conduction band. We draw this line. So we write this EC, which is the minimum conduction band. And here is the maximum valence band. So we just draw just one, line here, which corresponds to this one. This conduction band corresponds to this one. So this is two energy level. And then energy difference between these two, we call this band gap energy. Okay, so this one is, we can relate this with the work function, because this is a semiconductor. So we have a conduction band and valence band. We have a band gap energy for both, but these metals such as the gold and cesium, they do not have band gap energy. So we are talking about the work function. So if we can provide this, the energy, which is the work function for the gold, then we can emit the light, which is a photoelectric emission of electron for the gold. Okay, then yeah, this one is how it works. So electron in the conduction band and hole in the valence band. Then these electrons, they move to the valence band and they recombine together and they emit this band gap energy by photon. Okay, so this is a basic concept about this question. And then how we can relate these two? I mean, the work function, which is energy, and the wavelengths of this light, how can we relate these two? So this is a quite important concept. And we are using so-called Einstein equation. So this one is simply energy, which can be Joule or electron voltage. And H is a Planck constant. So we know the value, we know the unit. So they are in the formula list. And F is a 1/2 second, which is a frequency, how fast, the state is changed. And then, this one is further converted to this one. So we are using speed of the light here. So this is a still Planck constant. This is a speed of the light, and this is a wavelength of the photon. So we can relate the wavelengths and energy by using this Einstein equation. So further on to it, we can also use the unit to confirm whether they are correct. So here we are talking about the Planck constant. So what's the unit of the Planck constant? As you can see from the table, so this is a joule per second, joule times a second. This is a unit for Planck constant. And what is the unit for C, which is the speed of the light? It can be meter per second or centimeter per second. So this is a unit for light, speed of the light. Then what is the unit for wavelengths? So wavelengths can be nanometer or centimeter. So this is simply meter, we can say. So you can see second here, meter here, they are both in numerator and denominator. So we can ignore, delete it, right? The second they are deleted, and meter they are deleted. Then what do we have? So we have joule here. So HC divided by the wavelength lambda, the unit is joule, which is energy. The energy here unit also joule, or if we have an electron voltage, then we can convert from electron voltage to the joule, right? This is what we did the last class. So this question, you understand about the concept here about photon and the light emission in this direct semiconductor or from the metal. Then how can you relate these two concepts, which is the wavelength of the light and so-called energy? It can be work function or it can be a band gap energy. Okay, so this one is you can confirm by using this concept. Okay, then yeah, we assume you understand about this topic, and then we are moving to the solution part. So first one is maximum wavelength of the light for gold. So we are using this the equation, and then the value for Planck constant and speed of the light, as well as the unit, they can be found in the formula list. So you don't need to memorize it. Okay. Also, the Coulomb, which is 1.6 times 10 to the minus 19, is also in the formula list. Okay, so we look at the gold first. So gold, what is the work function, which is in the question. So work function for the gold is a 4.9 electron voltage. So this is energy here. Then we know the Planck constant from here. We know the speed of the light from here. Then we can calculate the wavelengths. Okay, so this is how we do. So first one, we try to convert the unit from electron voltage to the joule. You know the why, right? Because the work function is given in the unit of electron voltage, 4.9 electron voltage. But the energy we will use in this, the equation is joule, as you can see from the previous slide, right? The unit of the energy is a joule. So first step we need to do is we convert the unit from electron voltage to the joule. How do we do? We simply multiply the Coulomb here. So we multiply electric charge with this electron voltage, then we get the joule. Okay, so this one we do it a lot of times in our class, so please be familiar with this process. We multiply the Coulomb 1.6 times 10 to the 19 with the electron voltage to convert the unit to joule. Okay, so this is the first step. So we simply follow this relation. So this is what we know. The energy equal Planck constant times speed of the light divided by the lambda, which is the wavelength. So wavelengths can be just like this, right? Multiple by the cross, then this is what we get. So first one, this is h, which is Planck constant. So we just put it here, 6.626 times 10 to the minus 34 here. We put h here. The speed of the light, which is 3 times 10 to the 8 unit is meter per second. But this solution, we use centimeter per second. So we use 3 times 10 to the 10. But it's up to you. You can still use this. You can still use 3 times 10 to the 8, but you need to use the unit meter per second instead of centimeter per second, right? So this is a centimeter per second. And then here in this part, we put energy with the unit of the joule. So we put this to 4.9 times 1.6 times 10 to the minus 19. Then you check with the unit, then we have a centimeter. We have a cm here. Then this is just simple calculation. So you can use your calculator. We get 2.54 times 10 to the minus 3 minus 5 centimeter. Or you can convert to the micrometer, right? Because this is more simple. So it's also up to you. If the question asks you to use micrometer, you need to do it. But if they do not mention about the unit, it's okay to stop here, centimeter or meter. It's fine. Okay, so this is about the goal. You can check with the unit. EV here, we multiply by the Coulomb here. Then unit should be joule. This part also, the unit of Planck constant joule second. This is a centimeter per second. This is joule. So cancel each other. This is cancel each other. We have a cm, just like this. Okay, so it's a very good habit. If you're not sure, always good to use a unit to see whether left side and right side match each other. Okay, so cm. And for the session, we just repeat. The session has a different work function, which is 1.9. So we simply multiply with the Coulomb to convert the unit from EV to the joule. And the other part is exactly the same. So this, reduce the Planck constant same, the speed of the light same. This is a Coulomb, no change. Only this work function change from 4.9 to 1.9. Then you get this value, 6.54 times 10 to the minus 5 centimeter. You can further convert to micrometer. Okay, so this is our first question. Okay, so any question about this part?
Prof.
Okay.
From this question, right, can we come to a conclusion saying that that means for cesium, right, is a better medium for the emission of electrons? Can I say that if let's say in exams or like some theory question that happen to have this kind of question, can we come to a conclusion say that this cesium is a better medium for the emission of electrons because it
Okay,
travel
yeah.
further?
Yeah, that's a good question, but we usually do not discuss in that way.
Okay.
The way we describe is like because this one is if we convert to the nanometer, this is a 254 nanometer. So we call this ultraviolet. And this one, if we convert to nanometer, 654 nanometer, we call this visible wavelengths. So this one is what we can see. This is not something we cannot see. So usually based on these wavelengths, we determine by like the ultraviolet or visible wavelengths or infrared wavelengths. So this is usually the way we describe about the light. So we usually do not mention about easiness of the emission or like this.
Oh, okay. So for cesium is visible in terms of like okay, can understandable.
Yeah. So this one in the Google, you can check like wavelength light spectrum. If you Google it, there's some plot which show the wavelengths of the light and also how we call this like ultraviolet or visible wavelengths or infrared wavelengths.
Okay, can. Thank you.
Yeah, very good. Okay. Okay. Any more question? Okay, then let's move to the second question here. Okay, second question is more like the main part of our class today. So this one is a gallium arsenide, as you can see in the direct semiconductor EK diagram. So that's the material gallium arsenide. So this is a so-called bonding model for this gallium arsenide, which is described the gallium atom and arsenic atom, and they share 8 electrons as we saw in the previous slide. So previous class. So this question is more the concept question, like what happens if we insert, like if we remove this gallium and arsenic atom, and what happens if we insert the silicon atom in missing gallium and arsenic site? And in terms of the doping type, either N-type or P-type, whether this part and this part become P-type or N-type after we insert the silicon. So this is about this question. Then yeah, let's look at the content first. So the last week we briefly, mentioned about this material's intrinsic semiconductor. So what is intrinsic semiconductor? So you probably already know this. So intrinsic means that pure. So if this semiconductor is a silicon, we only have the silicon atom, not without any different type of the atom. So this one is we call it intrinsic. And intrinsic concentration, we simply use this, the shape like Ni. So this N is an electron, and this small I indicate the intrinsic case. So it can be Ni or it can be Pi. And what's the relation of these two? This one is intrinsic electron concentration. This is intrinsic hole concentration. As you can guess, these two should be the same. The reason for this here is like the electron, they are in the valence band, and they receive energy which is larger than this band gap energy from heat or the light, and they jump to the conduction band. So we call this generation, right? So here, the same number of electron and same number of the hole, they are generated by this generation process, always the same number. For example, if 10 electrons are created by this process, then 10 holes are created in the valence band. So this is how it works about the intrinsic constant semiconductor. Then what is the opposite to the intrinsic semiconductor? So you can already see here, we call this extrinsic, means that if this semiconductor is a silicon, we have something else like gallium, or we have arsenic, we have a boron within the silicon, then we call this extrinsic semiconductor. Then the next question is why we are talking about extrinsic semiconductor, why we intentionally put other types of atom inside the silicon. So this is a quite important question. Okay, you can think about it. So here, this is the plot we saw in the briefing slide. So the big difference between these three types of material is that this is a metal, right? This is an insulator. They have the dot, means that they have a specific conductivity or resistivity. They are fixed value, right? But in the semiconductor, as you can see in the middle, they have some range, means that we can intentionally change this resistivity and conductivity. So this is why we call this semiconductor, right? We can intentionally change this material property by doing something for certain application. So this is about it, right? So we intentionally put different types of the atom to change this resistivity or conductivity, and we call this doping process. Okay, so have you heard about this word before, doping? Yeah, some of you, maybe most of you probably heard about this word. So they are mainly used in like Olympic Games, like the doping test, right? So it's exactly the same concept. So what is doping test? So doping test is we test some athletic, whether they are using some illegal drugs to boost their physical performance, right? So this is the same. So we are doing the doping process for semiconductor, that they can change this kind of material property for certain applications. So this is about the doping from intrinsic semiconductor into extrinsic semiconductor, right? So this is about the concept. Okay, then now we are talking about the doping type. So as you know, in the semiconductor, we have two types of the carrier, which is electron and hole. So if we have a more electron, then we call this n-type because the electron is n. And if we have a more hole, then we call this p-type, just like this. And now we are ready to study about the mechanism, how semiconductor can be n-type, either n-type or p-type. Okay, so now we are relate this to, the configuration. So the left one, we know this, right? How we call this? Venn diagram, right? So we have a minimum conduction band here. We have a maximum valence here. And this is an energy difference, which we call the band gap energy. Okay, and then the right side is a atom and the electron, right? So here we have a silicon here, we have a silicon here. Then what happened here? So this used to be the silicon, but instead of the silicon atom, we have a P, phosphide. We call this phosphide, right? So here we have a phosphorus, right? Phosphorus. So we have a P here. Then what's the difference between silicon and P? So if you look at this, the periodic table. So this one is a silicon here. So we call this group 4. Then what's the valence electron of this material? You probably know this, right? The valence electron of the silicon should be 4, right? Should be 4. How about this? This is a group 3, like the boron, like the aluminum or gallium. So this line, this material has 3 valence electrons, right? How about this? Like the nitrogen or the phosphorus and like the arsenic, they are group 5, so they have 5 valence electrons. Then what happens if we combine these two, silicon and phosphorus? So I will just say P, right? So the silicon and silicon, when they combine, they make the covalent bond and they share 8 electrons, right? They share 8 electrons, so they are fully occupied like this. So this is an electronic configuration of single silicon atom. But by sharing these two, the silicon atom for covalent bond, they fill this remaining part. So they have 8 electrons, right? So as you can see here, they have 8 electrons. Or what else if we combine P and silicon? So here the silicon has 4 valence electrons. P has 5 valence electrons. So what's in total? So total electron number should be 9 instead of 8. And what happened? So we only can put here the 8 electron maximum, but we have 9 electrons, so we have additional 1 more electron, which is here. Okay, which is here. And we put this additional electron in the Venn diagram like this. So we have an additional energy line. We call this donor level, donor energy level. So we say this is ED, which is close to the conduction band, right? And this additional electron, which is created by this mechanism, they are positioned within this donor energy level. They are occupied by this electron, so we call this donor energy level. And then EC minus EV, which is the energy difference between conduction band and this donor energy level, we call this binding energy. Because these electrons, they are binded here, we need to supply the energy which is larger than this energy to release this electron, right? So this is about how we relate these two concepts. And this is when temperature equals 0. So this electron, they cannot get energy from the heat, so they are fully bind here, right? When temperature equals 0, and now we increase the temperature a bit here and a lot here. Then what happened in this case? We increase the temperature a bit compared to the 0 temperature. Then what happened to this electron in the donor energy level? You can imagine, right? Because these electrons in the donor energy level, they get energy from temperature, right? We increase the temperature, we are heating up this silicon, then these electrons in the donor energy level, they get energy from this heat, right? So here, some of the electrons in the donor energy level, they jump to the conduction band. And in rare cases, electron in the valence band, they also get energy, which is larger than this band gap energy, and they jump to the conduction band, right? So we have two different processes here. First one is this. Electron in the donor energy level, they jump to the conduction band, and electron in valence band, they jump to the conduction band. Now, what is the difference between these two? Probably in terms of the hole. So here you can clearly see that the electron in the donors level, they jump here. Then what happened in this donor energy level? Here just become plus, 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 plus here. But can you see the hole here? No, right? Because in this process, they do not generate the hole in this process. But what else here? The electron in the valence band jump to the conduction band, then they always create the same number of holes like this. So you can clearly see the difference. When they jump from the donor level to the conduction band, they do not create the hole, but when they jump from the valence band to the conduction band, they create the same number of the hole. So this is the two processes when we increase the temperature. So this one also, you can match these two. So this electron is what? So this additional binded electron, they are in the donor energy level, donor level. So they get energy from this temperature, they are released. So they are released, so they become, so-called free electron in the conduction band, right? How about this? So this one is the still binded electron, but in this covalent bond. You see the difference because this is an additional electron. This is an electron which are already there, right? So these electrons in rare cases, they also get energy from this temperature, but this is quite large. So they overcome this band gap energy. So they are released like this. So you can match these two. Okay, so this is what happened. How about this? So in this case, we increase temperature a lot. So in that case, most of the electrons in the donor level, they jump because this energy difference, which is EC minus ED, is quite small, smaller than this band gap energy. So most of the electrons in the donor state, they jump to the conduction band. This is also happening, right? So you clearly see the difference. Then now we focus on electron and holes. So can you compare the electron concentration in the conduction band and hole concentration in the valence band, which is larger? So in that case, as you can clearly see, electron concentration is much larger than hole concentration. So this is how we call this N-type semiconductor. So N-type semiconductor is like this. N0, so this is electron. Small zero means the thermal equilibrium condition. We will study this concept probably this week or next week. So N0 is larger than P0, which is a hole concentration. So this is how we call N-type semiconductor, as you can see here. And electron is major carrier. So we call this majority carrier is electron and minority carrier is a hole. Okay, so this is about N-type semiconductor, how it can be generated, and how can you explain about this? Okay, so this one. And then P-type semiconductor is exactly the same. So as you can see here, now we replace the silicon with the boron instead of P. Okay, so the boron, where is it? So this is boron, which is in the column 3 or group 3. So how many valence electron does this boron have? They follow the group. So this boron has 3 valence electrons. So what happens if we put 3 electrons here? So here 1, here is 1 here. This is right. This is 1 more, right? So we have a missing electron here, like this. So this is an incomplete bond. So this is corresponds to this acceptor energy level in the band diagram. Okay, you can match. Can you match this? We have a missing electron because the boron has a 3 valence electron, so one is missing. And in this band diagram, we use this acceptor energy level to indicate this missing electron, like this. So this acceptor level is close to the valence band. They are quite different. The donor energy level, which is close to the conduction band, but electron, they are already occupied here. But acceptor energy level, which is close to the valence band, maximum valence band, but this is missing. No electrons are here. Okay, this is also when temperature equals 0. So in that case, we also increase the temperature. Then what happened? So electron in the valence band, they get energy from this heat and they jump. They jump to the empty acceptor energy level, or they also jump to the conduction band, right? So this is more happening a lot compared to this one, because this energy difference, which is EA minus EV, is much smaller than this band gap energy, right? So the many electron, they jump to the empty acceptor level, and some of the electron, they jump to the conduction band. So here you can clearly see that this process is totally different from this, right? So when electron jump from the donor to the conduction band, they do not create the hole. But this case, when electron in the valence band, they jump to the acceptor level, then they create the hole concentration, right? So here, that's the difference. So we do the same. Can we compare the electron concentration in the conduction band and hole concentration in the valence band, which is larger? So this one, as you can clearly see here, hole concentration in the conduction band is much larger than electron concentration in the valence band. So this one is about this. So this hole and electron in the conduction band, hole in the valence band. That's the how we count the concentration. So in that case, hole concentration is much larger than electron concentration. So we call this p-type semiconductor, and majority carrier should be the hole, H here, minority carrier should be electron, right? So this is about intrinsic, extrinsic semiconductor and doping, how N-type and P-type semiconductor can be made like this, and acceptor energy level and donor energy level. So this is about the contents. Okay. Okay, so before we move to the solution part, any question about this? Doping and N-type or P-type. It's a quite important basic concept, so yeah, please try to understand. Okay, then yeah, let's move to the solution part. Okay, so yeah, this is a more like visual part, so it's not difficult, right? So please try to do it together. So now this is a bonding model of the gallium arsenide. So this is a gallium, this is arsenic. So how many valence band do they have? So here, gallium, how many? The group 3, so they have a 3 valence electron. How about arsenic? They have a 5 valence electron. So how many in total? 3 plus 5. They are fully occupy this, the energy, the electronic configuration. So gallium arsenide, they make the bond. They make the gallium arsenide semiconductor, and they are 8 electrons, so they are stable, right? So this is how we understand. So first one, we are removing the gallium atom. Then what happened? They used to have this 8 electron, 3 from where? 3 from gallium, 5 from arsenic. So what happened if we remove the gallium? Then we are removing 3 electrons, right? So here, out of 8 electrons, 3 electrons are removed. Then we have a 5 remaining electrons. So this one line corresponds to 1 electron. So this is a 1, 2, 3, 4, 5. So it's quite clear, right? We have 8 electron, 8 lines, but we are removing 3 electrons, 3 lines, so 5 lines are remaining like this. Okay, then it's up to you. You can put these 2 lines here and 1, 1, 1 here is also fine, right? It's up to you. And how about this? We are removing arsenic. So how many valence electron does arsenic have? So you can see here, arsenic has 5 valence electron. So we are removing 5 electron out of 8 electrons. So we only have 3 lines here. It's also up to you. You can draw line here and here, here, no problem, as long as we have 3 remaining lines. Okay, so yeah, this one, just like this. So gallium, how many electron, valence electron do they have? They have 3, so we are removing 3 lines. So arsenic, which column does they belong? How many valence electron? They have 5, so we are removing 5 lines. Then they have 3 remaining lines. Okay, so this is about the first question. So second question, we are replacing the silicon atom in this gallium site and arsenic site. So this one, what happened? So here we have a 5, 1, 2, 3, 4, 5. 5 electron. How about the silicon? How many electron? So silicon has 4 electron. Then how many? This is a 5, but we are adding 4 electron. Then how many total electron do we have? This is a 5 plus 4. So we have a total 9 electron, but available state is only 8. What does it mean? So we have 8 available state, but we have 9 electrons, so 1 electron should be additional, right? So here we draw just additional electron. 1 electron here, you can either draw here, 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 no problem, right? We have 1 more additional electron. How about this? So this is arsenic. So we have only 3 electrons because we are removing 5 electrons. Then silicon, they have 4 electrons. So 4 plus 3, then how many? They are 7, but we have 8 available state. So still 1 place, 1 line is missing because of this reason. Also, you can put 2 lines here, 1 line here. It's up to you, right? So this is how it works. So this one, this question, this is how we draw. And second question is silicon, gallium arsenide, they become p-type or n-type when silicon is replaced by the gallium. So this part, right? So this is a gallium atom. They are replaced by the silicon. Then what happened here? Do we have a more electron or do we have a more hole? We have a more electron, so this should be n-type. Okay, this is how we solve. This is n-type, right? Because we have additional extra electron is like this. Now, how about this? They become p-type or n-type when arsenic is replaced by the silicon. So here, it's exactly the same. So 1 line is missing. So missing line means the missing electron, then this is a hole, right? Missing electron is a hole. So this is p-type because there is a missing electron. Okay, so this is about it. So the important part is about how you can understand doping, how can you determine n-type or p-type, and how can you visualize in case of the silicon, in case of the gallium arsenide, when you do this process. Okay, so this is about it. So as long as you understand this concept, this part is something we can do, right? Okay, any question before we move to the last question? Okay, great. Okay, we are moving to the last question. Okay, let's look at it. Okay, so this question, we studied this concept in the lecture, so let's try to see how we can apply this. So we call this donor binding energy, right? We studied about this concept in the lecture. So donor binding energy for the gallium arsenide, the effective electron mass of the gallium arsenide is like this, 0.067 times MO, which is a rest mass. So this is simply mass of free electron, right? So this is much smaller. So Mn, small n is an electron. This star refer to effective, right? So this is a mass of electron in crystal. If we relate this concept to the previous, week, right? And also the relative permittivity of the gallium arsenide is also 13.2. So let's try to relate this. So this one is so-called binding energy of the dopant, and we studied in the lecture. So how can we understand this one? So as you know, in terms of the example of the hydrogen is that we have a proton here inside in the center, and there are electrons, they are circulating around this proton, right? And then we denote like this: the closest orbiter to the proton is, we call this n equal 1, right? This is n equal 1. The next one is n equal 2, 3, and the very far we call this infinity, right? So this electron is when n equal 1. So this is the innermost orbiter. This is the second innermost, third innermost. We go very far. We call this n equal infinity, right? So we try to imagine that because these electrons, they are binded, meaning that this is a proton, which is plus, this is a minus, so they attract each other, right? So it's like N and S magnetic. So they attract each other. This is why electron, they are circulating here and here. The binding energy is that energy, which energy required so this electron can be binded, right? Then if we think the other way, we try to remove this electron from the system, then how much energy do we need? This is about the binding energy, right? So this is the energy for the binding. If we want to remove this binded electron when n equal 1 or 2 all the way to the infinity, this is the energy we need, which is equal to the binding energy, right? So yeah, this is already, this kind of the equation is already established like this. Like this is a binding energy, and is corresponds to this number. Innermost, the second innermost, like this. And Q is a charge. We already know this. This is a reduced Planck constant. This is a permittivity of the vacuum. This is a rest mass. This is N. This is either N2, 1, 2, 3, 4, 5, like this. This is a reduced Planck constant. So this one is already established. So if you put the value here, Q, reduced Planck constant, rest mass, and permittivity of the vacuum, you will get 13.6 unit is electron voltage. So I know that some of you actually put detailed value here to see whether you get 13.6, right? Yeah, you can try, but yeah, I got some question from some student in the previous batch is that they found the values are a little bit different. But in the case, yeah, please trust that this value is already established. You can try, but this is already, the established value. Okay, so then how we apply this concept in the gallium arsenide? We just do the same, like the Coulomb here, reduced Planck constant, no change, because they are same value for different material. The only different value for different material should be the mass. So instead of the rest mass, we use effective electron mass here. Instead of the permittivity of the vacuum, we additionally multiply this relative permittivity value. So entire permittivity value, we multiply these two. This is a permittivity of the vacuum, which is a fixed value, and this is a relative permittivity value for different material. So this one for silicon, gallium arsenide, and germanium, they have a different value, but they are in the formula list. So you can capture that value from the list. And these two are different, right? Mass and the permittivity, because we are talking about specific semiconductor, which is gallium arsenide. At N, still no change, right? Because N indicate like orbital identifier, so they should be the same, right? So if any question asks you to solve this binding energy, then you can simply use this formula to calculate, right? So this is about the concept. Okay, so difference is a mass, also permittivity. Okay, right? So we can apply this concept in this question. So we simply use this binding energy. Okay, then we replace this part with this one because they are given here 0.067 times rest mass. So we put this value in here. Then also relative permittivity of the gallium arsenide is a 13.2. So we put here 13.2 here. Then what happened? Just like this. Because this part, if you go back, this part, like the Q4 square, reduced Planck constant square, rest mass, and also permittivity of the vacuum, they are 13.6, right? They are 13.6. So additional one is this one, relative permittivity square, and this is also 0.067, and other part is a 13.6. Okay, so here 13.6 from the previous part we already discussed, and Mn star is this one 0.067. So we put here, and 13.2, which is a relative permittivity of the gallium arsenide square. So we put 13.2 square like this, and then this 3 is a simple calculation. So we get 0.0052 divided by n square electron voltage. Okay, so this one. Then how can we estimate the calculate donor binding energy? So in that case, they do not mention about n, right? They want to remove electron from n equal 1 to infinity or 2 to infinity, 3 to infinity. They do not mention here. So in that case, what we assume is that when they mention about this donor binding energy without mentioning n, then we usually assume this case, like from the innermost orbiter to outermost orbiter. So we used n equal 1 for the innermost orbiter. We use the infinity to the outermost orbiter. So if we put n to 1 to n here, what happened? 1 square simply 1, so we have a minus 0.0052 electron voltage. Then how about this? When equal infinity, we put infinity here, then it becomes 0. So here, so this energy difference is a donor binding energy because we need this amount of energy to remove electron from n equal 1 to n equal infinity to the outside. Okay, so we focus on this energy difference between n equal 1 and n equal infinity. So it simply becomes like this, 0.0052 electron voltage. So this one is so-called donor binding energy. Okay, so this is about the concept, how we can understand this donor energy of the dopant, and can we actually calculate this donor binding energy for specific semiconductor, which is a gallium arsenide. Okay, so this is how we calculate. Okay, so any question about this question 3? Okay, so yeah, I will upload this, and if you have any question, you can always welcome to contact me, right? So yeah, based on that, the next question we are touching this concept, like can we actually calculate electron or hole concentration by using this concept, density of the state, Fermi-Dirac distribution function. It should be more interesting, but a bit difficult, right? So this is a topic we will study next week. So please try to solve the question before you come. Okay. Okay, before we end the class, any question? Okay, good. And then this recording is already downloadable from the Teams. You can do it. Or I will also upload this recording and slide in the Angular so you can watch it. Okay, thank you.